So it's actually lecture 9. We continue with the WKB approximation. In the previous lecture, we applied it to the classically allowed region, and now we apply it to the classical forbidden region. Well, actually, I will just claim more or less that what we derived in the classical allowed region, so that P was actually a real number, has mathematically the same, or pretty much the same expressions, also for the classical forbidden region, where P is imaginary. Yeah? So far, so let's go back to a few slides here. Let's go back a few slides here. So you see that this P so ends up. So this P ends up in the exponential, of course. And in the exponential, it's decorated with the imaginary unit, which means that we have an oscillating function. Now, when this thing here becomes imaginary because the energy is smaller than the potential, so when this here is imaginary and we multiply it with the imaginary unit, then we get a real exponent. So we get something that decays exponentially, well, which is just what we expect from tunneling. Yeah? So we are confident that we are doing the right thing, in other words. So now I just need to remember which number we are at. We are at chapter 3.6. Should I start a new page? Let's start a new page. So 3.6. The tunneling region. The tunneling region, meaning that the energy is smaller than the potential. So far, we had P is a real number, so this momentum is a real number, which means an oscillating function, or an oscillating psi, right? So now we have that. Perhaps I should write this a little bit more detailed. We had P element R because E is larger than V, right? Now we have, now E is E is smaller than V, and this means P is imaginary. Right? And what we expect is an exponentially decaying psi. Yeah? Well, let's write it down. Yeah, so let's just write it down. And if we write it down, then we might think about what I just have written once again. Yeah, so we have e to the plus minus 1 over h bar. And now I write here the magnitude, perhaps p of x, right, to make this clear. So you see that I have now a real exponent. Yeah, so I multiplied that already out. Therefore, I write. So initially I had I over h bar and so on, but we know that this here is imaginary, so I multiplied I with I, so I have 1 over h bar just in front of the integral. Okay, so what you see is that we not only have an exponentially decaying function, but in principle we also have an exponentially increasing function, right? So it's a linear it's a linear combination of both. Yeah, so, but of course, we know physics, and we'll discuss this exponentially growing function. We'll exclude it. So now we consider a generic tunnel problem. Yeah. So in principle, yeah, so in order to get 12, we are just doing the same thing as we did in chapter 3.5. One would need to look at whether all the conditions are fulfilled, but they are actually. So I don't want to spend time on that. So now we look at a generic tunnel problem. Yeah, so we have a tunnel barrier which has an arbitrary shape, and we just look on how things are going. So we consider a generic tunnel problem namely the square potential, actually not precisely the square potential, so the square potential barrier. So something, we consider something like the following. We have it's first the coordinate axis, right? And we assume that we have a potential that looks like this here. And to make it a little bit more general, we just make it not exactly a rectangular, but we give it a arbitrary shape. In any case, it starts here at the coordinate 0 and ends here at the coordinate A. And what you see is that we have three regions here. Right, so, and we call these regions 1, 2, and 3. It is very simple to find the solution for 1 and 3, because this is just a constant potential, and we already said, so in my introductory remarks to the previous lecture, I indicated, or I said what the solution is. We actually made this ansatz of a plane wave and plugged it into the Schrödinger equation and found that it is fulfilled. So what will be the solutions? So let's assume that we have an incident wave, matter wave, incident psi here in region 1. Then it's clear that, well, something will tunnel, and we get something over there. But also, we know that something will be reflected. By the way, if we look back on this page here to the very beginning here, so you see here k equals this square root, blanks off again, k equals this, so I mean, doesn't work. Yeah. So just before the headline 3.5, you see this expression. Yeah. So k is of course 2 pi over lambda, and you see how it depends here on this on the potential. Yeah. So for a given energy, and now you can look at this problem, or at a wave, at a matter wave in a potential. You can make an analogy to a photon and a refractive index. So you can directly translate this into a refractive index. Yeah, so what this means here, this potential barrier that we have here, is that we have a refractive index step. And you all know that when we have a a changing refractive index that that a certain fraction, which is given by the reflection coefficient, is reflected. So, and actually, well, waves are waves. So what holds for optics also holds for matter optics. Good. So now we solve this zone by zone. So for zone 1, 2, and 3. And we do the simplest ones first, zone 1 and zone 3. So in zone 1, we have an incident and a reflected wave. So therefore, the wave function in this zone 1 is given by, of course, the linear combination of both waves in opposite directions. So e to the plus ikx plus b e to the minus ikx. In zone 3, there is no reflection. So therefore, we have just the plus solution. So zone 3, we have, I call the amplitude f to the ekx. Yeah? Well, and now we can already say what the tunnel probability is, because we have here these two amplitudes, right? So we have here this amplitude A1, and we have here the amplitude F. Yeah, so here the amplitude for the incident wave A, and here F. So let's write that down, A and F. Right? And the intensity, the transmitted intensity, is of course proportional to the square of the amplitudes, and therefore we can write down an expression for the tunneling probability. So the tunneling probability, we write down the tunneling probability is the probability that a particle gets transmitted. Yeah, so is the ratio of incident intensity in optical words, right, and transmitted intensity. So in other words, we call this tunneling probability capital T. This is equal to the magnitude squared of F divided by the magnitude squared of A. Equation 13. Yeah, so and the only thing that we would need to know is how A and F are connected. Yeah? So this means the only thing that we need to know is how psi 1 and psi 3 are connected. Well, and of course, they are connected by the wave function psi 2, right? Of course, the answer is psi 2. So therefore, the logical next step would be to write down the solution for psi 2. We said it's an exponentially decaying or perhaps an exponentially growing function. Well, we would say if the tunnel is of of reasonable size, it will be the exponentially decaying part. Yeah? So psi 2 consists of an exponentially decaying and growing term. Well, and the larger the barrier, the smaller the exponentially growing term, the larger the barrier, the smaller the coefficient. I'm not sure whether I wrote it down above. Let me check. Let me check. I didn't, I'm afraid. Yeah. So the larger the coefficient for the latter term, for the exponentially growing term, and this means that we assume that the exponentially growing term can be neglected. Yep. And this means that we would write psi 2 as d over, again, square root of the magnitude of x, and we have e to the minus 1 over h bar. We integrate from 0 to a, I would say, the magnitude of the momentum dx. Yeah? So that's equation 15. Now, we can say how this looks quantitatively. So let me copy this thing here, this little figure here. I want to copy it, but it doesn't work. Ah, yeah. So here we have it. Maybe I can delete this thing here. Right. So what we have now is an incident amplitude, so something like this here, right? Oh. Something like this. Here, this here would be the amplitude A. Right, then we have something that comes out here, and in between it decays like that. Right, so this here would be F, this amplitude. So this is how it should look like. Well, and with this, yeah, so this looks now a little bit ugly. So it looks like as if we would need to do these continuity or these steadiness conditions here and fit all these wave functions to each other. But actually we don't need to do that because it's basically equation 15 only that gives us, it's basically psi 2 only that gives us that ratio. We just need to evaluate this here at this point and at this point, and we are done. Yeah, so from this we get already the ratio of F and A. So let's write down that. So even without using continuity of psi 1, 2, and 3. We can specify the ratio. Well, we kind of use it, yeah? So even without explicitly using the continuity of these three wave functions, we can specify the ratio of A and F. Yeah? It's basically using, of course, continuity. So it's just given by this function here, e to the minus 1 over h bar. We integrate from 0 to a px dx. So that's equation 16. Okay, well, we are done. We just define this, we just invent a new symbol for this integral, which makes it a little bit nicer to write it down. Yeah, so we define this here as gamma. And this is, of course, the decay constant, right? So we define gamma is equal to 1 over h bar, and this integral here of p over px magnitude, and then the tunneling probability looks very simple. It is given by e to the minus 2 times gamma, yeah, because it's the magnitude squared of the ratio of f and a. Good. So that's equation 18. So great, isn't it? Did we learn anything? Yeah, maybe. But in order to, we should also apply it. Right? So let's apply it to field ionization, to exactly this thing in the classical model, which is kind of outside the classical model, namely this first step, how the electron gets into the continuum, so field ionization. Good. We look for field ionization. I think we are at chapter 3.7. 3.7. So here is the other material so that you can still have a look at it. 3.7. Application to field ionization. Yeah, and it is always comforting if one can derive these formulas that we find in the literature, and this is actually what we want to do. Actually, the Coulomb potential is kind of too complicated for, at least for me. Yeah, so you're invited to do it yourself. But for me, it's too complicated. Therefore, I resort just to a delta potential. Yeah. Okay. So, for the sake of simplicity, we solve the problem for a delta potential. Yeah, then it looks like the following. So the following. We have a delta potential, which, let's first draw the a coordinate system. Yeah, so something like this. Yeah, so we have x here. We have, of course, the potential energy in y direction. And now we have a potential, a field-free potential like this. Field-free potential like this. There's a delta potential, which I indicate like this. Would go to minus infinity, but never mind. So this would be the field-free potential. What I also should mention is actually the ionization threshold. Right? So this is the ionization threshold here, EIP. So we would then have a wave function that sits here like this. Right? And now the potential where we do have a field, then it looks like this. Yeah, so the combined potential of field and atomic potential. Yeah? So this is here the combined potential of atom and external field. And here we assume that E is equal to 0. Right? Okay, what we need to do is to integrate over the potential barrier. Yeah, so we need to integrate kind of over this thing here. And what we called A is now this point here. Yeah, so this is A, and here is 0. Okay. Yeah. So and now in order to calculate A, so compute the tunnel exit A. The tunnel exit A. Yeah, the condition is, of course, that minus x times E. Right, so this here is minus x times E, minus x times electric field. This must equal the ionization potential. Right, so this is equal minus the ionization potential, which means, of course, or rather I should actually write here A. Yeah, so, which means, of course, that A equals ionization potential divided by electric field in atomic units. Yeah? So, and what we need to compute is clear. Namely, we need to compute this gamma, right? So this means that we need to compute this integral. So we need to compute this integral from 0 to A over px dx. Right? And what we know is that px is equal, by definition, to 2m times E minus V, and now I write here explicitly V of x. Yeah? Which means, which in this case means that P of x, for E we plug in the ionization threshold. Yeah, so EM, EIP minus Vx. No, minus x times E. Yeah, so this is here Vx. So EIP minus x times E. Yeah, so we assume here a constant field. So, and this results in gamma equals 1 over h bar. And then we integrate from 0 to a, but for a we found EIP over E. And we have 2m times ionization threshold minus, well, this dipole interaction here. Yeah, and then we have to integrate that. And because I don't know how to do that, I just asked Mathematica. Yeah? I was too lazy. Yeah? I'm sure you can do it quickly. What we get is EIP to the power of 1.5 divided by 3 times the electric field strength. Equation 19. Equation 19. Yo. Yeah. So the question was, so that's also for those on YouTube. The question was, what is this length of the tunnel as compared to the excitation wavelengths? So this question implies a misunderstanding. So what we assume here is a static electric field. Yeah, so the question for of an excitation wavelength or the wavelengths of the laser is ill-conceived. Yeah. So and actually, this is what we this is actually the decisive thing in strong field laser physics, that we make the so-called quasi-static approximation. That we assume that the tunneling is much faster than the oscillation period. Whether this approximation is well fulfilled is another question still, right? Most of the time in most experiments that have been done so far, in reality, this is actually not well fulfilled, I can also say. But in physics, we are used to approximations. Yeah? So in any case, the approximation we make in strong field approximation. So really, thank you for this question. This is an important point to make. And throughout this lecture, I was always thinking at which point I would emphasize this. And of course, your question is a good occasion to do that. Yeah, so in strong field approximation, we say if that at a certain instance of time, at a certain instant during the oscillating pulse, the electron tunnels, which implies that we assume that the tunneling is a fast process. Yeah? And therefore, we assume that while this tunneling takes place, the field is constant. Yeah? And therefore, also the headline here, application to field ionization. So field ionization actually assumes that we have a constant field. So, for example, like you would have in a tunneling microscope. Yeah? So there you would apply a certain voltage to your tip, which at a certain distance, if the tip is at a certain distance from the surface, would create a certain electric field which is constant, right? And then you have a certain tunneling rate, a certain current, a certain tunneling current. So the question is, if the field, the laser field consists just of a few cycles, still, yeah, so we look at an instant, at a small fraction of the cycle. Yeah? So even for half a cycle, we would do the same thing here. Yeah? Yeah, so, and actually this is the key point, how strong field laser physics gives access to the attosecond region. Yeah, so remember, the lasers we are using, they have an oscillation period of 2 femtoseconds, 2.5 femtoseconds. If you go to the infrared, even longer. And on first glance, there's no way, there's no gate to the attosecond region. But now that we have this thing, that the tunneling time, if we may speak of tunneling time, so that the electron somehow appears, well, through the tunneling process at a certain instant, yeah, within the phase, within a single cycle, and that we can actually have access, experimental and also theoretical access to that. This is the gate to attosecond laser physics. Yeah? It's a cool approximation, right? So that we speak of attoseconds, and we treat it as field ionization with kind of an infinitely long, with a constant electric field. Next question.
Yeah, is the square root of 2m divided by h bar, like, do we now switch to atomic units?
Yes, we switch to atomic units. Whenever it's convenient, we just switch to atomic units. Yeah, sure. Yeah, so I probably made a small remark here at this point. Yeah, actually, I'm doing this constantly to switch between. Whenever I'm tired of SI units, I just use atomic units. Yeah, so as long as we derive something and all these prefactors are not so disturbing. But as soon as I have to calculate something, I just throw them away. Yeah. So I fully understand if you don't like it.
No, I was
yeah.
Just because, like, on the one side of the equation we still have them, and then on the other side we have one. I was wondering if you dropped all the constants, like
yeah.
The square root of 2m.
So you mean basically here at this point, right? Yeah. Actually, in my script, I still have the remark atomic units. Oh. Good. Yeah. Okay. So we are almost done. We want to talk about the tunneling probability. So far, we have just gamma, but we need the square of that. Yeah, so what follows is that the tunneling probability, which is e to the minus 2 gamma, and therefore we have the exponential of minus 4 over 4 times the square root of 2 times the ionization potential to the power of 1.5 divided by 3 times the electric field strength, E. Okay, yeah. So we have a nice expression for that. And now that we did that, you may be encouraged to also do the Coulomb potential, at least numerically. And I did that. For the Coulomb potential, you need to pay a little bit of attention, right? For the Coulomb potential, there may arise the following complication. So the Coulomb potential looks, of course, like that, field free. Yeah, so something like that. if we apply an electric field, then, so I should also show here the ionization thresholds, perhaps something like that, so the ground state level. And now if we apply a certain field strength, then it perhaps looks like this, right? Perhaps something like that, approximately. And then, of course, this here would be the area over which we integrate. But what can also happen, if you make the field really strong, what also can happen is the following. So if we apply a really strong field, then we may have the situation. We may have the situation. We may have this situation, right? So, which means that there is no tunnel any longer. I'm not sure whether Matthias discussed that. Barrier suppression intensity, I think he discussed that, right? And then, of course, we are lost here with this approach, right? And accordingly, so we should not calculate, we should not use these expressions for this situation here. Okay, I did this, these calculations. I plotted, so I plotted this expression here, and I want to show the result to you. Yeah, so this is how it looks. So I used here different ionization thresholds, and I did it for the delta potential. This is here shown in blue, and I did it also numerically for the Coulomb potential, which is easy enough. So, and you see here I have 0.5, which would correspond to the hydrogen atom. Well, what I have to mention here, a big side remark, we are doing here a one-dimensional atom, right? And there, whereas real atoms are, of course, three-dimensional, so the shape of this tunnel of this tunnel is in one dimension. It's quite simple. But if you try to imagine how this looks in 3 dimensions, then of course in field direction the cross section is perhaps like this. But as you go away from the field direction, the tunnel barrier gets larger and larger, right? So it's much more complicated in 3 dimensions. But of course you can use parabolic coordinates, and then it's basically also a one-dimensional problem. Okay, so this is kind of the one-dimensional hydrogen atom here. Not a real hydrogen atom, but a one-dimensional hydrogen atom. So in 3 dimensions, the effective kind of ionization energy would be larger. And what you see is that this here would be the decay rate. And the same thing for the Coulomb potential. I made the same graph in logarithmic as a logarithmic plot, and there you see the complication with the Coulomb potential. So maybe I shift this around here a little bit. So this is the same thing here now on a logarithmic scale, and you see this exponential, this gets a line. You see how much they deviate for the same ionization potential. Yeah, solid curves, or dash curves, and so on and so forth. Right? And you see, of course, that this here would be the intensity where this thing happens, where the barrier gets suppressed. Yeah, so this happens here at a little bit more than 10 to the 14 watts per square centimeter. So the formula is E. Do I remember that? So E squared over 2 or so. Yeah, E over 2 squared or something like that. Yeah, and this way you can calculate the intensity. Okay, well, one final graph here is now to calculate the tunneling rate. Yeah, so the inverse, so to say, right? Yeah, which is of course quite interesting, because if you have a pulse that's 10 femtosecond long and the tunneling rate would be a tenth of that, yeah, then you would know that you get into saturation. Yeah, so here the tunnel rate in 1 over femtoseconds. Right? Then if you multiply it with the pulse duration and you get something on the order of 1, you would know that the ionization is saturated. Right? And here you have the 10 femtosecond. So here it would be 10 femtoseconds. And depending on the intensity, you see whether you get saturation or not. No. It means so the longer so we always speak of a certain probability, right? And let's say the probability of ionization, or the rate of ionization would be 1 over 10,000 per femtosecond. Right? Then if you have a 10 femtosecond pulse, the probability that after these 10 femtoseconds the atom is ionized is 1 over 1,000. Yeah? If it is 1 over 10, it's 10 to, if it is 10 to the minus 4 per femtosecond, then for a 10 femtosecond pulse, it would be 1 over 1,000. If you have a nanosecond pulse of the same intensity, then the ionization would be almost sure, right? So would be the probability for ionization would be close to 1. Yeah, next question.
How do we get to this per femtosecond? Because we just had, like in so far, we only had one wave, and then we calculate how probable it is that this wave will end, like the particle associated will end up on the other side. Do we multiply with like more frequency, or?
Well, if you look at this, these are we have atomic numbers here. This gamma. This gamma is per time. Yeah, so it is. We have a constant electric field, so we get a probability per time. We get a rate. Yeah, and here I transferred this to SI units. Okay, I think we stop at this point and reconvene next week again. Thank you.